So statistical inference is where you're using the data, the statistics, to infer something. So we use our data analysis to make some sort of conclusion about the probability distribution. And then we'll assume that all sets of data has that same thing. So we usually will sample a data set and then make predictions about the whole population. Why do that? Why sample rather than just look at the whole population? The population, if it's finite, I suppose theoretically you could gather every piece of information. But you might have an infinite population. It might be impossible to gather the whole thing. So why do it? It's certainly going to be quicker. It's quicker just to survey a sample rather than get every possible piece of information. It's going to be cheaper. And this is the more interesting thing. It's actually more accurate to look at a sample rather than the whole population. And the reason for that, we're human. So the more bits of data you gather, more chance there is of making a mistake. Writing a number down wrong or something like that. So it's actually more accurate to do a sample. Necessity. Right? You can't test for quality on things. The classic example there is matches. Let's say you were interested in knowing, in my batch of matches, how many are defective? Well, how are you going to tell whether a match is defective? Oh, I'll light it. Now, you do that with a sample, that's fine. You go through a sample, how many didn't work? Do that with every one of your matches, fantastic. You'll work out how many didn't work, but now you've got a pile of matches that you can't use. So not practical, not practical. How should we get our samples? Always randomly. And randomness is not necessarily an easy thing to do, but it should always be random. What does random mean? It means every piece of data has an equal chance of being chosen. It could have been any one. So if I was in this class, that every one of you had the same chance of being chosen, I just happened to randomly select these few. So there's no bias. There should be no predictability about how I picked them. Problem is, there still is a problem with that. Because a random sample is not necessarily going to give me a cross-section of the population. Let's say it is our class. And here's our class. I want to get a sample. Now we've got 24 people in here. So I'm going to randomly select 4 people. Is it going to give us a good cross-section of the class? Well, let's say, we happen to get everyone off that back table there. We just randomly picked it. We ended up with those 4 guys over there. Now, is that cross-section the same as the whole population? I mean, you can find all sorts of reasons why. Well, 3/4 of them are wearing a tie. But, yeah, there are obvious other reasons as well. All right, so terminology that goes with these two ideas. If you are gathering the whole population, then we don't call it a survey, we call it a census. But if I'm just grabbing a sample, that's when I call it a survey. So a census is when you gather every possible piece of information. Now, when we're talking about probability, here's where the difference comes in. Probability is when you have every piece of data. So with the population, we call it probability. With a sample, we actually call it relative frequency. The expected value, and someone brought this to our attention the other day. What's X bar mean? Well, there's the difference. Mu is the symbol we use when we're talking about the population, X bar, the sample. Deviation, or actually variance I've got there. So variance, sigma squared that I was using there, population, S squared when it's the sample. Now what we should find happen as n approaches infinity, so as the number of pieces of data in our sample gets closer and closer to infinity, then they should end up being equal. We should be getting closer and closer to the actual answers. So all right, I'm going to use this as an example to show you what I mean. 2 dice are rolled. We're going to use the theoretical probability to work out the expected value and variance for the population. So I'm going to sample it. Here are the probabilities for rolling 2 dice, but I've done them to 4 decimal places. And so the different sums we could get, 2, 3, 4, up to 12, of course. Okay. And then I've also worked out the xpx, and I've also worked out the x squared px. The expected value of the population is 7. So if you roll 2 dice, you are expecting to get a total of 7. There is, of course, a variation on that. It's about 5.83 repeater, which means the deviation is about 2.4152. Okay, so that's the population. If I was to plot it, you get a lovely little graph. It's nice and symmetric, but there's the graph. So now what we're, well, sort of not going to do, but we're going to do, we're going to roll a pair of dice 50 times, then 100 times, then 500 times, then 1,000 times, and let's see how those different samples compare with the population. What we should find is as that number gets bigger, it becomes closer and closer to those values we just found. Do not fear, I've already done the rolling of the dice for you. And I actually got a computer to do it, I didn't physically do it myself. Okay, so 50, here were the results. So I've got on the top the population, and then frequency is what happened when I did a simulation of 50, how many turned out to be. So let's work out our results. The expected value of my experiment with 50 was 6.42. So I'm about 0.58 away from the expected value of 7. The variance turned out to be 5.8036. So when I compare the standard deviations, that's pretty close in this case, 0.0061 difference. Plotting the data, so the diamonds there were the actual ones, the crosses is where the experiment ended up. So, bit chaotic up the top there, not too bad. Right. Let's see what happened with 100. So there's the results for 100. 7.16 is the expected value for that particular sample, out by 0.16. Variation, or variance, 5.95, out by 0.0250. That's interesting, because the difference with the standard deviation in the last one was actually a lot closer. There's those two graphs compared. All right, 500. 6.86, we're out by 0.14. Deviations out by 0.0394. Have a look at our graph. Okay. Now I promise you this was purely random, because I'm looking at this as I remember when I was doing it going, a bit disappointing. Those ones have ended up. But it is what it is. I'm not going to change it, because then it wouldn't be random if I changed it. I'd be forcing the data. So we came to 1,000. I got to be honest, I was a little bit pleased with this one. So 7.042. So it's out by 0.042. The deviation, 0.0619. But look at that graph. I thought that was pretty good. Look, it's random. I could have got a different set of numbers out there which would have made that graph look completely different. But that's the whole point about sampling. I mean, you just do what you do. There are different formulas statisticians use to work out how many bits of data should I collect to get the best sample and things like that. Okay, you'll notice I've only picked 4 questions out of 13D.